Welcome back. I used the wrong title in the last lesson. I had all this. I had put integrating inverse trigonometric functions. No, integrating functions that lead to an answer in inverse trigonometric functions. I think that's the correct way of looking at it, because integrating inverse trigonometric functions I will do separately later. I don't want to mislead you with my title. So please, I can't change the title in the previous lesson because the video has already been recorded. So this same title goes back to the other one. Now, last lesson I did how to use this formula, and I also taught you how to complete the squares. I want to now do method of splitting numerator. They may not say this in the exam. Of course, my friends from Edexcel, unless the syllabus has changed in June 2000, no, it didn't change at all. So maybe next year this might be useful. Otherwise, at the moment, people doing Edexcel A-level maths don't have to worry about these questions. Alright? Splitting the numerator. Suppose I had integral x plus 5 over x squared plus 9 dx. Now, if it was only 5 over x squared plus 9, I could use this formula. It is only x over x squared plus 9, I could use numerator's derivative of denominator. But unfortunately, it's a combination of both. In this case, what we do is, look, the derivative, always recognize the numerator, it's a fraction, algebraic expression or rational expression. But then in the denominator, I have x squared plus 9. When I differentiate, I get 2x. I have an x in the numerator, but I have an extra nuisance, the plus 5. You can't say, look, just get rid of minus 5. No. Split it into 2. So can you write this as integral x over x squared plus 9 dx plus 5 integral 1 over x squared plus 9 dx. So I have split the numerator. Okay. Let's look at the first one. I'll write the answer in the end there. So integral x times x squared plus 9. I don't have to do that. X over x squared, there's no root, x squared plus 9 dx. It's an algebraic fraction. What the rule when it's a rational expression? Always check whether it's a proper fraction. How? The power of the numerator must be less than the power of the denominator. That's power 1, that's power 2. Good. Next, differentiate the denominator. What do you get? X squared plus 9, when you differentiate, you get 2x. What do I have in the numerator? X. How will I make it 2x? Make it 2x because remember, you can multiply or divide by a constant, not a variable. So multiplied by 2, so I write a half. Here, the numerator is the exact derivative of the denominator. Integral f dash of x over f of x is ln. So it is half ln x squared plus 9. That is that integral. Let's look at the other one. Integral 1 over x squared plus 3 squared dx resembles 1 over a squared plus x squared. In place of a, you have 3. So it is 1 over 3 arc tan x over 3. So the question becomes half ln x squared plus 9 plus 5 over 3 tan inverse x over 3. In the exam, they will not tell you split the numerator and integrate. It is for you to analyze and figure out. Okay. Let's take another example. It's not always this simple. Integral 3y plus 8 over y squared plus 2y plus 5. Okay. What do you get when you differentiate y squared plus 2y plus 5? Of course, let's do it the same way. When you differentiate y squared plus 2y plus 5, you get 2y plus 2. I have 3y plus 8. So what do I do? So remember, d by dy of y squared plus 2y plus 8 is 2y plus 2, which is 2 times y plus 1. I don't have a 2. I can bring a 2. I need y plus 1. I have 3y. And I can't remove 3. I can remove 3 forcibly as a common factor. It becomes a mess. See, y plus 1 could also be 3y plus 3, couldn't it? With 3 as a common factor. So, I'll write this as 3y plus 3 plus 5 over y squared plus 2y plus 5 dy. Why did I do it? When I differentiated the denominator, I had the numerator which contained the y plus 1, but it had something else. So first I want to recognize where is that y plus 1. So this becomes 3 times y plus 1 over y squared plus 2y plus 5 plus 5 over y squared plus 2y plus 5. I have now split the numerator, but the way you split the numerator is by identifying the derivative of the denominator. Be careful. So that becomes 3 integral y plus 1 over y squared plus 2y plus 5 dy plus 5 integral. Now, that one now, I can complete squares because it's a quadratic. If you have a quadratic at the denominator and no derivative in the numerator, complete squares. This is y plus 1 whole squared plus 2 squared. I will leave it to you great minds to figure out how I completed the squares. Here, when you differentiate the denominator, I get 2y plus 2, which is 2 times y plus 1. I have a y plus 1, I don't have a 2. So can I bring a 2 and divide by a 2? So this will lead to, let me write the answer here. So that will lead to 3 over 2 ln y squared plus 2y plus 5 plus 5 times, this is 1 over x squared plus a squared. In place of x, I have y plus 1. When you differentiate y plus 1, you get a constant. So I can integrate directly. So that is arc tan y plus 1 over 2, 1 over a, your a is 2, plus c. You understand that? That is the next question is pretty interesting. So, whenever you have a numerator and generally a quadratic in the denominator, differentiate the denominator, adjust the numerator to have the variable part of the derivative and then split the remaining and split it into 2 integrals. It comes by practice, it comes by observation. I can only show you how to do it. I can't teach you how to think. Some of you are much faster than me, you can think much better than me. So let me take another example which makes life a bit more interesting, as I will show you here. Boom, boom. Integral 3 minus 7x over square root of 4x minus x squared. What you get when you differentiate 4x minus x squared? 4x minus x squared, when you differentiate, gives you 4 minus 2x or 2 times 2 minus x. I need 2 minus x, but I have a minus 7x, right? So if minus x becomes minus 7x, that should become 14, which is 7 times 2 minus x, right? So I have minus 7x, I need a 14, I have a 3. So can I write this as, first let's write it as 14 minus 7x. How much have I added? 14. How much should I take away to get the 3? So minus 11 over root of 4x minus x squared dx. Do you understand the logic? You differentiate the denominator, remove common factor, see the variable part is 2 minus x. I have a 7x, so when this minus x becomes 7x, I need to multiply by 7, so I'll get 14 minus 7x. So I wrote 14 minus 7x, but I needed a 3, so I took away 11. So you adjust the numerator before splitting. So let me rub all this. So I can rewrite the question as integral 7 times 2 minus x over 4x minus x squared power half minus 11 integral 1 over square root 4x minus x squared dx. Yeah, that is the tricky part, to adjust the numerator to reflect the variable part of the denominator, and there is a root, so it's not even an ln function. So let's do each one separately. So at 7 integral 2 minus x times 4x minus x squared power minus half dx. I'm going to use inspection, but you can use substitution. U is 4x minus x squared, so du by dx is 4 minus 2x or 2 times 2 minus x. I have a 2 minus x, so I'll write it as 7 over 2 times integral 2 times 2 minus x times 4x minus x squared power minus half dx. Some of them are wondering, thank God I didn't do for the math. Or thank God I didn't do OCR, or let me let you into a secret. I taught in England for 16 years. And I personally like the Edexcel is a great syllabus, no problem there. But I wanted this to be introduced at A level instead of in further maths. And I always used to fight, let's do these questions, even though it's not in the syllabus, let's do it. No, I was told, sorry, don't confuse the students, stick to what is in the syllabus. Fine. Of course, I didn't manage to. So now this is, if this was u, all this would become du. I'm using inspection. So u power minus half gives you u power half over half. So they cancel. So it is 7 root 4x minus x squared. So I'll write that 7 root 4x minus x squared. See, integration is so challenging, at the same time so interesting. I love integration. And then let's look at the other one. That would be a 10-mark question. because there's quite a bit of work to be done. Now I have integral 1 over root 4x minus x squared. So a minus bx plus c the whole squared is 4x minus x squared. A minus b squared x squared minus 2bcx minus c squared is 4x minus x squared. So minus b squared x squared is minus x squared, so b is 1. Minus 2bcx is 4x, so c is minus 2. A minus c squared is 0, so a is 4. So once you do all that, so it becomes 4 minus x minus 2 the whole squared. So I can write this as integral 1 over square root of 4 minus x minus 2 the squared dx. That 4 I'll write as 2 squared. It's like 1 over a squared minus x squared. Arc sine x over a. No, yeah. So therefore that is minus 11 arc sine x minus 2 over 2. Interesting? The next question is more interesting. And now we go from simple to complex. This is a technique which I show you, yeah, which you can use. Remember this, a cos x plus b sin x over p cos x plus q sin x dx. If you have a question like that, and you have to integrate it, splitting the numerator. But then I don't know anything about a, b, p and q, but I know this. When I differentiate a cos, I get a sine. Of course, that's a negative. And when I differentiate a sine, I get a cos. So the numerator seems to have the variable part of the denominator. So this is what you generally write. Numerator equal to k times denominator plus, what should I use? Okay, a times denominator plus b times d by dx of denominator. So whenever you have a question like this, I don't think you will come across that, but that's a very wonderful concept. So whenever you have a cos x plus b sin x over p cos x plus q sin x, not cos 2x, sin 3x, cos 3x, sin 4x, no. It has to be cos 2x, sin 2x, cos 2x, sin 2x. Yeah? Because otherwise life becomes very complicated. So therefore, let me take an example to show you what I mean. I have it here. Integral 3 cos x minus 2 sin x over cos x plus sin x. It could even be just only 3 cos x. The numerator is a part of the derivative, so it still works. Or if I go back to what I was saying, I said a cos x plus b sin x, either a or b could be 0, but p and q cannot be 0. So numerator equal to a times denominator plus b times derivative of denominator. Yeah. What's the advantage? You will see once I complete the question. So if I compare the coefficients, 3 cos x equal to a cos x plus b cos x, giving me a plus b equals 3. Similarly, minus 2 sin x equal to a sin x minus b sin x. So a minus b equals minus 2. Add a is half. subtract 2b is 5, b is 5 over 2. Alright? That means this I can write as integral a is what? A half times cos x plus sin x plus 5 over 2 times minus sin x plus cos x over cos x plus sin x dx. It's a long time since I taught this. I always enjoyed doing this. So therefore, let's split them into two integrals. It is half integral. Oops, did I go wrong? Oh no, cos x plus sin x over cos x plus sin x dx plus 5 over 2 integral minus sin x plus cos x over cos x plus sin x dx. That is, I am trying to stretch you a bit. Here you see they cancel. I get half x. Here the numerator is exact derivative of denominator. So 5 over 2 ln cos x plus sin x. In fact, if this question comes in the exam, it could as well come in an edXL exam or OCR or any other board. Says show that cos x plus sin x equal to find a and b such that cos x plus sin x equal to a times cos x plus sin x plus b times minus sin x plus cos x, and hence or otherwise evaluate integral blah 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 blah. You see? Then you follow the same procedure. So I hope you enjoyed looking at maybe some of you are grateful that you have missed out. I want to show you some questions on special substitutions. Okay? I'll see you in the next lesson. Bye-bye. Hello. I want to take this opportunity to propose a vote of thanks. I would like to thank Vivid Innovations Private Limited and Commerce Forum for so generously giving up their studio and the facilities and the services of their technicians to record all these videos for free. I think that needs to be acknowledged and appreciated. Thank you very much. And my special thanks to Mr. Nitin Mahadevappa, Mr. Nishant Guruswamy, and Mr. Sadan Kumar DN for all their help and assistance in getting these videos ready, uploaded and launched. Thank you very much.